So I think we will be able to finish the common emitter topology today. Okay, and then common base, common collector, we will see if we can do it today, otherwise in next class again we can do it. Okay, so what defined the three topologies, common emitter, common base and common collector? Let's see that. So if I say, so some of you might already know this, but I'm still going through it. Okay, um, just 1 second. Yes. Okay, so common emitter, then base, and then collector. Okay, so common emitter, common base, common collector. What defines it is, if you ground the common emitter, okay, if you can say that the input and output is not from the emitter. Okay, so so basically emitter is the common part. So emitter is common. That is why it is called common emitter. Okay, so neither the input nor the output should be from the emitter. So if I say that this is my BJT, okay, this is the BJT, then you know that this is base, this is collector, this is emitter for NPN. Now for PNP, what it will be? Same thing. This is the base, the arrow part is the emitter, and then the collector. And we have seen how to take the direction of current and how to annotate the voltage, that we have seen in the last class, right? So I'm not repeating that. So now the NPN, PNP, you know. Now what happens is, suppose if I take the BJT and I put the input to the base, connect the any input to the base, and I take the output from here. So when I say this, that I connect the input to base, take output, what I mean is, I take a function generator, let's say external function generator, and I connect it, physically connect it to the base. And here I take it and physically connect it to an oscilloscope. Or if I am only playing around with DC, then I am connecting a DC source maybe here as an input, and I can check the output with a multimeter, because multimeter is an average voltmeter, right? Multimeter shows you the DC value. So this is what I mean when I say input and output. Okay, so keep that in mind. So if your input is in the base and if your output is from the collector and your emitter is not taking part in this input and output thing, it is a common thing. So if we see the small signal model of the BJT, we will understand what is meant by the common emitter. Common, the word common. So suppose if it is grounded, or in some cases you will see a resistance attached to it, anything is possible. In this case, this is a common emitter. Similarly, in base, what happens? In common base, the base is common. It is either grounded or any other source is connected to it. But your input will be from emitter and your output is from collector. This is common base, CB configuration. Okay, and common collector is similar to common emitter, but now the output is taken from the emitter. As I had mentioned, that the output, it depends on where you are taking the input and output from. So if the output is from the emitter and input is in the base, then this is the common collector. Okay, so the same circuit which you would have designed for a common emitter, that can work as a common collector as well. So this is the input. If from here the output is taken, this is common collector, and if from here output is taken, it is common emitter. Now obviously when you are taking the output, you are taking from any one node, right? So if you take the output from this node, it is common emitter. If you take the output from this node, it is common collector. Now we had a very interesting question in gate. Okay, and I think I had solved it in some of the last classes, that they had given this circuit, the same circuit they had given, and they have asked you, so this was A, this was B, and they asked you VA minus VB. And this was such a nice question that you did not do a lot of solving thing in this. What you had to do was, if you take the common in the same circuit, okay, if you put your oscilloscope pin in the point A, you will get the output as per a common emitter configuration. Whatever is the voltage gain of common emitter, as per that your output VA will be decided. Suppose the input is 2 millivolts and the gain in emitter configuration is 100, then VA is 200 millivolts, because in common emitter the gain is directly multiplied. But when I say what is the gain when the output is from VB, then VB is from common collector and it is, the voltage gain is always 1. We will see that. And in that case, the output is 2 millivolts. So if I ask you what is mod A minus mod VB, then the answer is 198 millivolts. So I can directly do that. I don't need to do anything else. It was not any, like, if someone doesn't know the concept, it is a confusing question for him, because he will think, oh, what is it? Is it common emitter or is it common collector? The question should not come in your mind. It entirely depends on from where your output is taken. The same circuit is going to behave as a common collector as well as a common emitter. They are just terminologies. Okay, they are just terminologies. Like you can say, how should I give an example? Like you are right now a student, or let me take my example. So I am a PhD scholar. I am the daughter of my house also. I am teaching you guys in NPTEL PMRF TA whatever it is. So I am performing 3 roles, but I am the same person. So it is just like that. Your circuit is already connected. Now from wherever you will put the oscilloscope or the multimeter, the output will come across the terminal depending on the behavior of the circuit. Okay, so we will see this example in detail. I will see if the question is still there, or I will else make this question and show it to you. We'll see it in some time. So let's start with it. So I think now you have a basic idea. So if you want, I can write down the summary. Input, output. Okay, common emitter. Input is base, output is collector. Common collector. Input is base, output is emitter. Common base, input is emitter, output is collector. Okay, so this is the summary. You guys can write it down. Okay, so just quickly write it. I'll go to the common emitter topology now. Okay, so if I write it in a two-port network type, if you remember from your network theory, in two-port networks, something like this is drawn and there is a back blocks, and there is one terminal which is pointed out as ground. So you can say that input and output, if I compare it with the common emitter or common collector thing, then this is the base, this is the collector, and the emitter appears in common between the input and output port. Okay, emitter is common between input and output ports. That's why it is called common emitter. Same for the other three, likewise. Okay, so just quickly take a photo or draw it. Next, we will start the small signal model. So today we will take a 2-hour session, so 4 to 6, and what we will do is we will finish the entire common emitter thing, common emitter configuration, common emitter with degeneration. You will be able to draw the small signal model as well. You will be able to solve questions without drawing the small signal model as well. We will see what is the effect of base resistance. We will see what should be input resistance ideally, what should be output resistance, what is early effects. So I'm not going to explain you early effect, but when early effect is present, what happens to the output resistance, where those kind of circuits are used, okay, why a high output resistance can be desirable, okay. So these things we will just have a look into, okay, so that if theory questions are also asked in multiple choice things format, you guys will be able to answer it. Okay, so from here let me move forward to the small signal model. So small signal model. So small signal model, I want you guys to solve it, okay. I want you guys to do this solution, okay, because it's easy, it's not that difficult, okay. So what we have is this transistor, right? So I am now not using any emitter resistance, and I hope you guys remember from the bias class which we took in last week, we saw that the stability point of view from stability point of view we solved the circuits, and we saw why emitter resistance is put, right? Okay, so now we will see, and I had told you that there are some problems with this emitter resistance putting, and we will see when we see the amplifier, so we will see that as well, okay. So now this is my circuit, okay, this is the V out, this is RC here, this is VCC, okay. So right now in the circuit you can see that so this input V in, this will be a DC plus AC input, okay. Why DC? DC will bias the circuit, and what will AC do? AC is the small signal basically which you have to amplify and see at the output, okay. So now if I say how the small signal can be modeled or represented, so what is meant by modeling? So if I say there is a resistor, when I say there is a resistor, what you have in mind is, okay, this will follow Ohm's law, V will be equal to I into R. So this is the model of the resistor, V equals to IR. This is the model of the resistor, okay. So now how will the BJT behave? How will the BJT behave? So I know the physics of BJT, but when I solve the circuit, will I use the entire physics? Will I keep on thinking about the entire physics and do the BJT's question solution? No. I should have a equivalent model that will tell me how BJT behaves, a mathematical model, okay. And that is why small signal models are used. So small signal is nothing but if a small varying signal around DC, if the variation of the signal is small, then that is called a small signal, okay. So small signal model, if I use such a signal whose variation across DC is small, and that kind of a signal is put into BJT, then how the BJT will model itself. Just like if I now go to IIT Kharagpur in my lab, I will behave as a research scholar. Okay. Now, if I come to my house, I'm no longer a research scholar. I behave the way my surrounding is, right? So, just like that, in the BJT, if you put the input, which is a small signal, then the BJT's model will behave in a particular way. So, let's see what that particular way is. So, for a small signal, the BJT model is like this. Now you see inside the box, inside this dotted line box, this is your BJT. Okay, and you can see that the terminals are coming out of it. So if I try to draw it more clearly, let me draw it more clearly. Okay, So this was the base, this was the collector, this is the emitter. Okay, now inside you see this R pi and this current source is not physical. I did not buy a resistance and a current source are connected to make a BJT. I did not do that. This transistor you see here, is what will behave like this if there is a small signal put in its base input. Okay, and therefore I will redraw this. Okay, I'll quickly redraw this. So this R pi, this current source, they are not a physical quantity. Okay, remember that. Now, where is the input put? The input is from base to ground, right? So therefore, I have put it like this: plus minus V in to ground. Emitter is already grounded, right? So emitter is grounded. GM V pi. Where is this V pi? So GM V pi is a dependent current source. It depends on some other voltage or current which is generated in any other part of the circuit. So here it is a dependent voltage current source. Okay, dependent voltage. V pi is that independent voltage where this current source is dependent on. Okay, and this is generated across the input resistance R pi. And this one is the collector terminal which is connected to RC, you can see. Now, when you make a small signal model, this is also called the AC analysis, and whenever you do the AC analysis, all the DC sources are shorted. So, this one is shorted to 0 volts. Now, this V in was DC plus AC. So, even if the DC is shorted, that is 0 volt, the AC remains. Okay, that's why V in is there. So, this is from collector terminal. You can see this collector terminal and ground. The RC is between collector terminal and ground. So, RC is between collector terminal and ground. And the collector terminal itself is the V out. This is the common emitter configurations small signal model. Now, I want you guys to quickly tell me what is the value of V out by V in. So, please solve it and then tell me, because you guys might remember the answer already, but I want you to solve. So, V out upon V in. Take 2-3 minutes, put KCL equations or KVL equations, whatever you want. Tell me the value of V out by V in. Please solve it. Please solve it, okay? I'm giving you guys 2 minutes. Please solve. Whoever is new to this topic as well as whoever are old, it will be a revision. The answer is GMRC, that you already know, right? Many of you would have already know this. Okay. So let me just quickly solve it for you. Anybody who has solved it, just raise your hand. I just want to see if you guys have solved it or not. Can you please raise your hand here? So I just want to see your participation. So Hari Prasad, Jayesh, have you solved it? Did you get V out by V in? Are you facing any difficulty? You can unmute yourself and tell me. So how do you solve this kind of a thing? This is network analysis now. So if you guys have not done network analysis, please do that first. Networks is the first subject to do. Networks and signals. Okay. So let me just tell you how to solve this. So in this kind of a circuit, if I ask you what is V out and V in relationship, so you don't see any direct thing between the two, right? So what you do, this node is V out. This you have understood, huh? This is V out. Now this is V in. Here it is easy to apply KVL, and here it is easy to apply KCL, because the node, there is a common node and a current source. Therefore easier to apply KCL. Okay. So now what is KCL in the output? So KCL at output, what will it give? So V out by RC, take all the currents to be outwards. Okay. V out by RC plus GM pi is 0, because here it is an open circuit, right? I am not connecting anything, so I am considering this as 0 amperes input. So GM pi plus RC, V out by RC is 0. So therefore V out is equals to minus GM RC pi. But you wanted between V out and V in, right? So you wanted between V out and V in. So now you have to, for V out and V pi, so what you can do, the input gives you the relation between V in and V pi, and the output gives you the relation between V out and V pi. So if V pi is common, then you can get the relation between V out and V in. So now you apply the KVL at the output, KVL at input, and what you get? So how do I apply KVL? My way of applying KVL is, while entering, if I take this direction as I, current I, so if I enter a negative sign, I write minus V in. And this is the correct direction, right? This is the direction. So here when I am entering, I already have a plus minus V pi. And if I am entering, I am encountering plus. So I will directly write it simply as plus V pi. You understood? When I enter, when my current enters a negative terminal, I write minus and then the voltage value. And then across R pi, if across resistance, if the voltage is not given, suppose their V pi is not given, in that case whatever is the value of current in the same direction, I simply write it. I don't use a sign. And then you just, here since plus V pi is already there and my current is entering plus terminal, I am writing plus V pi, and then from here I go to E 0. So from ground to ground you reach in KVL. So V in is V pi. You understood? I should not be explaining this to you here, but anyways, V in is V pi, and therefore V out is nothing but minus GMRC into V in. Therefore the gain mod V out by V in is GMRC, and without mod the sign is negative, indicating that the phase is opposite. This is the voltage gain. So is it clear? Please response. Is it clear? I understand that for many of you it might be a very childlike thing, but others who don't know, I just wanted everything to be clear. Okay, so this is how you apply. So let me quickly give you an example of a KVL thing, so that after this, if you guys have to solve the problem, you should be able to. Okay, this is not a part of my job, but still. So suppose R1, R2 is there, and here V is there. Okay, and I have to find current I, and the direction of current I is already given. Okay, so what you do? See, the current I is going like this, right? So that means current I is going like this. So when if current I is entering negative terminal, I write minus V. My direction of current is this. So plus I R1 plus I R2. So drop across resistance is always positive. That is my convention. Okay, equal to 0. So V is I into R1 plus R2. Now suppose in your question it is said that find current I, and the direction of current I is given like this. They have given it like this. Okay. So now you have two methods to solve this. How you can solve it? The first method is, you take your current to be in this direction. Suppose you are letting this connection. Okay, so whatever your value will come, the negative one will be your answer, because that is already given in the question. You understood? The second method is you just take the same value of current I, which is given in the question, and then you see this current is entering positive terminal. This is entering positive terminal. So you will write plus V plus I into R1 plus R2, right? Equal to 0. So you see automatically your value of I is coming to be negative. You understood how KVL is applied? Now the another thing which can be asked is that they will already give you a voltage like this and say VR. Find VR. So what you will do? You will take a current direction. You get the value of current, right? And then VR will be what? If the current is entering the plus terminal, then VR is positive. So IR2. That's it. You understood? So solve a few questions. Go to SADQ, network by SADQ. Solve network question from here. Use this convention. You can never do any mistake. Okay. With this convention, mistakes don't happen. I hope this is clear. So now I will go back to my thing of the small signal model, where we have already got our values of voltage gain, GMV pi, there was RC, this is also grounded, this is R pi plus minus V pi, this was Vn. Okay, so now we already have mod AV, V out by Vn. That is GMRC. Okay, so now let us see what is Rin. So Rin will be input resistance and input voltage and input current division. So if we have a two-port network like this, then Vin by In is Rn, right? Vn by In is Rn. So what is Vn by In here? So In is nothing but this current, which is equals to Ib, because this was the base terminal as well. So what do you see? Vn in In, you can simply put a KVL here from this ground to this ground, from this ground to the emitter ground, KVL. So this will give you what? Vin equals to In into R pi equal to V pi, which we have already seen. So Vin by In is nothing but R pi. Okay, done. Okay, now okay, now we will see output resistance. So how do you find output resistance for a two-port network? For a two-port network, the output resistance is found by, we apply a source here, VDC, and the current due to VDC is IDC. And what we do, any other independent sources should be 0. So here the independent source is Vin, that is 0, and if there is a current source, that is open circuited. Okay, so independent current source is infinity, open, and voltage source is 0. Okay, so VDC by IDC will give you the output resistance, which is nothing but the Thevenin resistance as well. So now in this circuit, I'm doing it in the same circuit. If I put V in as 0, then what happens? V pi is also 0, right? If V pi is 0, this GM V pi is 0. And therefore, if I have a VDC and IDC here, the entire IDC current will flow through the RC. And thus VDC by IDC is RC, which is the output resistance. Now, if there are any other resistance in parallel to RC, it will be in a parallel combination. So please quickly write all this. So let me just remove the unwanted explanations. So only mugging up doesn't help. Okay, you will have to understand whatever is being done. Okay, so I hope now it is visible. So please have a quick look and then we will proceed. We'll proceed with some examples. Should I proceed? Please let me know.
Yes, ma'am.
Okay. So now let us do an example. Okay. Please write down the question. What is the value of RC for achieving maximum voltage gain with VCC equals to 1.8 volt and a power budget P of 1 milliwatt? The circuit is the same as the one we had discussed now. So, sorry. This is the circuit. The power is given as 1 milliwatt. VCC is 1.8. I'm giving you 1 minute. Try to solve this. So take VBE to be 0.8 volts. So when will you get a maximum voltage gain? So take the condition of transistor being at edge of saturation. Okay. So take the condition that VCE is equal to VBE. Okay. So in this case, it will be just 0 volts, right? So VCE minus VB is 0 volts, which is VCB 0 volts is your edge of saturation. So take this condition and now tell me what value of RC and AV you are getting. RC and voltage gain. Please solve this. I'm giving you 2 minutes. And if you get any answer, you just tell me, okay? I want this to be an interactive session. Did anyone finish? It's a simple thing. The value of power is given, so first find out IC from it. Okay, and if you have IC, you already have GM, and then you can find RC with the edge of saturation concept. So giving you 1 or 2 minutes more, then I will solve this. So the power is given as 1 milliwatt. Okay, and what will be the total power? It is VCC IC, right? IC is the current drawn by the BJT, and VCC is your supply voltage. Supply voltage into supply current. So VCC into IC is nothing but 1 milliwatt. Okay, VCC is 1.8. This is 1 by 1.8 milliamperes, right? IC. Okay, then you find GM, IC upon VT. So 1 upon 1.8 by 26, this much ohms. Okay, and RC is what? RC will come from the condition of edge of saturation. So VCB greater than 0 is for active region. So VCB equal to 0 is your edge of saturation. Right? So VCB equal to 0 is edge of saturation. That means VC equals to VBE. That is equals to 0.8 volts, because I have already given you VB is as 0.8. Just see it. Let me rotate this, I think. Yeah. Okay. This is how I'm moving forward. So now VC is equals to VBE equals to 0.8. Right? And therefore what will be RC? RC should be anything which is less than equal to VCC minus VBE by IC, because that voltage drop has to be less than the voltage drop of VCC minus VCE. So let me write VCE first, then otherwise you will get confused. VCE, and then I am putting the values 1.8 minus 0.8 upon 1 upon 1.8 into 26, this much ohms RC. So solve this and tell me what you are getting. RC is less than equal to what? Okay, 47.6 is not the correct one. I'm just checking my calculation once. So I see if you calculate from it, it will give you 0.556 milliamperes. Then 0.556 milliamperes upon 0.026 volts. This will give you 21.38 milliampere per volt. Okay, then here I give 0.556. Oh, IC, I had written it wrong. Okay, I had written GM in place of IC. So please correct that. So 1 upon 0.556. Yeah, it is 1.8. Thank you. So RC should be anything less than equal to 1.8 kilo ohms. I had by mistake written the value of GM in place of IC. Okay. Okay. Now if you find AV, what it is? It is minus GM RC. Tell me what is the AV? Minus 21.38 into 1.8. Okay. This is the solution. Now there is a concept to be explained. Okay. So this I hope is understood. So this kind of thing can be asked. Okay, please. So should I keep it? Or do you want to note it down? So let me keep it for 1 minute. Okay, and after that I will put another explanation which is very interesting. Please let me know once you have written it down. Okay, and please be quick so that we can finish it today itself. Is it done?
Yes, ma'am.
Okay. So now remember this result. Okay, AV is minus 38.5. Let's say minus 38.5. Okay, remember this. Now suppose I am now saying that in this BJT, so listen carefully to this explanation. Okay, this was RC, this is VCC. VCC was 1.8, and I said that edge of saturation में VCE is equals to VBE, right? Now for the small signal, what is happening? So this is the same as your VBE, right? So I'm just putting V in here. Okay, so now what I'm taking VBE to be, VBE is also 0.8 and VC is also 0.8. Clear? Now that means this DC is 0.8 at input. At input, this DC is 0.8 and I am having a small swing, let's say of 2 millivolts. 2 millivolt peak to peak. So if I am taking 2 millivolt peak to peak means this is 1 milli, this is 1 milli. Clear? So that means this is what? This is what? 0.8. 0.8 volts. That means this is 0.802, this is 0.8. sorry, this is 0.801, this is 0.801. Any doubt here till now, whatever I have written, or should I repeat? I'm saying 2 millivolts peak to peak. So this is VBE, right? The base voltage. I told you, right? The input is a combination of DC and AC. So this DC is 800 millivolts or 8 volts. And I'm saying that the small signal is 2 millivolt peak to peak. So if the small signal is 2 millivolt peak to peak, that means it is going 1 millivolt in positive half up, 1 millivolt in negative half down. So 801 millivolts and minus, sorry, so this is the wrong. So 800 minus 1, 799.799. Please just interrupt me if I write something wrong, okay? So 0.801 is up voltage, positive voltage, and in downwards it will come to 0.799. Okay, so this is how your input is looking. Now what will look into, how will the output look? Your AV is now minus 38.5, right? So 38.5 into 2 minus 77 will be your minus 77 millivolt peak to peak is your output. And what is the DC? DC is VCE, right? DC is VCE. So 800 millivolt, just like the input, and 77 up, 77 down. Because of the minus sign, it is phase shifted by 180 degree. So this is 877 and then 800 minus 77. Let me check. 800 minus 77 is 723. Till now, is it clear or any doubts? This is how your Vout will look. Why is Vout looking like this? Why is it across 800? Is it clear? This is important. Is it clear?
Yes, ma'am.
Yes, ma'am.
Clear, right? Okay, good. Now you see that what is base voltage maximum value? 801. Huh? So 801 being the maximum value and output's maximum is 877, huh? Or 723, whatever you want to take. 723, huh? So 801 and 799, this is 877, 723. What is this? Vout is nothing but VCE, the smaller VCE, and this is smaller VBE. Now to be in active region, what I need? I need VCE to be greater than VBE, so that VCB is greater than 0, right? So that means with this condition, even with the edge of saturation applied, I get a gain of 38.5. With this gain, my transistor is still in amplification region and therefore it can behave as an amplifier. What will happen now if I try to make the gain high? What will happen is that the transistor may come out of the active region in saturation region, and then the output waveform will look something like this. It will clip off. We will see in next example. Till now, did you understand what I am saying? So it is very important. Three things are very important. First is your voltage gain, that is in middle. Now as you are trying to increase and decrease the voltage gain, how will you try to increase and decrease voltage gain? Voltage gain is GM-RC. You will either play around with GM or you will play around with RC. If you play around with RC, that is the output impedance. If you play around with GM, that will affect your input impedance. And all this playing around will change the voltage gain, which will in turn change what is called as a voltage headroom or voltage swing. You would have heard about this. Voltage swing or headroom. So what limits the voltage swing or headroom? Whatever is the drop across I into RC, right? If the drop of IRC is low, your VCE is high. And if my VCE is high, that means My waveform can tolerate more swing. It has more headroom to move around so that it doesn't go below VB. Did you understand this point? This is not much discussed, but this is a very important property.
Please repeat, ma'am.
Okay. So what we want to make sure is that VC should be greater than VB. Okay. And therefore, VC is decided by what? It is decided by the limit from VCC. What is VCC can supply? So now suppose if I want to increase the voltage gain, I will increase RC. But if I increase RC, the drop across RC will increase. Therefore, VCE will reduce. And now if VCE reduces, okay, the headroom reduces. The voltage can now swing between that reduced VCE so that it still remains in active region and doesn't go into saturation. Okay, this can be seen with the help of another example. Now, suppose I say VB is at 800 millivolts. Okay, just like before. VB is at 800 millivolts. The swing is 2 millivolt. 801 799. Just as before. But now I am saying that you know what? I am increasing the value of RC because I want to increase my gain. Okay. I'm increasing the value of RC because I want to increase the gain. So what I'm trying to do is I will make VCE as 400 millivolts. So if VCE is 400 and this is 1.8, that means the drop across it is 1.4. Now with 1.4 volt drop, okay, and the same IC, 0.55 something, 556. What are you getting? Tell me. What is the value of RC you are getting? Check. You will get 2.52K. That means earlier what was RC? RC was 1.8 kilo ohms. RC earlier. Now RC is increased to 2.52. What will happen if GM is same? GM is same as before. What was GM before? GM was 21.38. 21.38 milliampere per volt. Now what is AV? 21.38 into 2.52. So 21.38 into 2.52 will give you 53. So 53.8776. Right? So now my voltage gain has increased. Earlier my voltage gain value was what? 38.5. Earlier voltage gain was 38.5. Now voltage gain is increased because I increased RC by decreasing the VCE. By decreasing the VCE. Right? So now if my VC is 400 millivolts and VB is 800 millivolt, it is clearly in saturation region. It can no longer amplify. And what will happen? How? Now it will go around 400 millivolts. Output. I'm talking about output. And how much will it go? 2 into 53.8776, which will give you near around, I think, 108 millivolts. Okay. So now you see this is going at 508. This is going 400 minus 108 something. Right? And it is still VCE becomes less than VB. So the amplification action will not be there. This will not look as a sinusoid. It will clip off. Okay, because it is no longer in active region. So this is what is voltage swing or headroom. So you need to maintain the proper voltage headroom so that your BJT is in active region. Okay, and proper amplification is there, faithful amplification, to ensure faithful amplification. Okay, So this is what is the importance of voltage headroom of finding the VCE. So there has to be a limit, right? You can keep on increasing RC. You can keep on increasing RC to increase voltage gain. You can say, ma'am, I can just make RC higher and higher, and that should increase my voltage gain. But no, what will happen? Your device will come out of active region because the drop across RC is also increasing when you're increasing RC. Okay, and that will make what? The drop across VC small. If VC is small, it is smaller than VB, game ends, no amplification. Understood? So please remember this. This is important for your theory as well as your objective type question. They can give you waveforms at the output, and one of the waveforms might be clipped, and you need to identify that whether clipping will happen or not, whether voltage headroom is satisfied or not, like that. Okay, more questions are there in Razavi's book. You can solve it. I think an exercise there should be there. Okay, please solve it and show that your concept becomes clear. Okay, so now let's do another question. Okay, I hope this is clear. Okay, so if it is too much to take in, then please after this class solve a few problems. You will understand what I'm trying to say. Okay, or you can watch some more video lectures from NPTEL. They would have definitely discussed it because this is an important point. So please go through it. Voltage headroom is what is limiting your value of RC. We're limiting the voltage gain. Okay, so now please solve this question. IC is given, RC is given, beta is 100, VA is 10 volts. So what is VA? VA is something which comes from early effect. Okay, so I'm not explaining what early effect is. So because of early effect, we have a internal output resistance, which is R0, and that is given by VA upon IC. And the small signal model that you have seen, that will now have this R0. Okay, rest of the things are same. Okay, so now what will happen? So with this R0, first let us see what is the okay, let me just solve it. I don't think you should solve the numerical without solving this. So let me just solve the small signal model first. Okay, so this will be your VN. Here there is RC. This is grounded. Right? Now you can see from here the total resistance is what? RC parallel to R0, and therefore your voltage gain will now be equal to GM minus GM RC parallel to R0. Is this clear? Your output resistance will be RC parallel to R0, R out, and that's why AB is also called as capital GM into R out, where GM is the entire transconductance of the circuit and R out is the entire output impedance. So here in this case, capital GM is nothing but small gm, and capital R out is RC parallel R0. So this you can write. So this capital GM, capital R out concept is what will be majorly used in quickly solving the questions. We will see that later. So please write till here. Ignore the side questions. Those are to be done after this. So please ignore that, but just write down the rest of the things. Now with this background, I think you can solve the question. So I won't solve it. You guys have to do it. Okay. Let me just, okay. So now this was the question, okay. Don't see this. Huh? This is the question, and this is what you have to solve. So please start solving. IC is 1 milliampere, RC is 1 kilo ohm, beta is 100, VA is 10 volts. Now what is beta? Beta is nothing but GM pi. GM pi is also can be also termed with beta. Okay, so please solve it. You have to find input output impedances. So for finding input input impedance, you will need beta. I hope the question is clear and you are not confused. Let me just move it down a bit, otherwise. Okay. Please tell me the answers if you have solved. It is clear, right? No doubts. R naught is the output impedance because of the presence of early effect. Early effect is base width modulation. Okay. Because of the application of collector to emitter voltage, there is a modulation of the base width, because of which the current collector current will change. So that is an additional change which is not anticipated, but it comes because of the physical nature of the VGT. And therefore that is modeled as a small r naught. The small r naught is given by VA by IC. VA is early voltage, and that is counted as a parallel thing between collector to emitter. That is a R naught is between collector to emitter. But in this case, since the emitter is grounded, the R naught is coming in parallel with capital RC. It won't happen if the emitter is not grounded. We will see that in capital RE when the emitter resistance is present. So please solve this. Tell me the values. IC is given, VA is given, RC is there. Take VT to be 26 millivolts. So first find GM, IC by VT. You can find RO, VA by IC. From beta is GM R pi. So you can find R pi from here, which is the input impedance. Output impedance Z out. Let me write R out. So Rn, then Rn will be what? Rn will be R pi. R out will be RO parallel with RC. We just saw. And then AB will be minus of GM into RO parallel RC. You got it? Just don't look into it and mug it up. Just see from how I have written the sequence. Please find the answers. What is the value of GM? Anyone? In milliampere per volt? What is the value of GM in milliampere per volt? RO in kilo ohms? Please be quick, we have to start emitter degeneration as well. Okay. I asked you in the milliampere per volt. So, uh, okay, right. You guys are right. 38.4. Okay. What is RO? 10K. Okay, good. So, what is beta? Beta was 100, already given, right? So, then what is R pi? 100 upon 38.4. 2.6K. Good. What is RO parallel with RC then? Okay. Then AV? 34.96 minus. So now see, when you are solving this problem, if you don't write it in terms of 38.4, then also it is very good, because like in case they have not asked it, if you are simply solving it and your final goal is AV, then you simply write it as 1 by 26. Just remember your unit. Now you see, when you are finding R pi, this is just have to be 1 over it, right? So 1 over 1 by 26 into 100. So you directly get 2.6. So you need not use your virtual calculator again and again, because that limits your speed. You understood what I'm saying? And in most of the numerical answer type, they will give you questions where you can directly get the answer. Mostly in IES exam, they give you such kind of questions where you actually don't have to go up to decimal places, because they don't allow calculator, right? So you guys should practice it in that way that you need minimum calculator usage. Okay, great. So we have solved this question. Let's go to the next part. Okay, so now we have to start degeneration. Okay, so let's start with common emitter degeneration. So last class we have seen, so first we will see why it is called a degenerated resistor. And last class we have seen that to increase the bias point stability, that is to keep the operating point at the place where the maximum amplification is possible, a reliable amplification is possible, we put the emitter resistor, because the emitter resistor actually absorbs the variations in the input. Okay, so what is happening? Suppose now this was the BJT, right? Now there is a small delta V variation in the input, uh, uh, like whatever is the reason. Now this delta V variation, this will appear as a small variation in VBE, okay, and if there is a small variation in VBE, then IC will also vary by a small amount, and therefore your output voltage changes. Now if this variation is because of the temperature variation or due to any external noise, then that affects your VB. That is an unnecessary output. So what we do, if we put a resistor, just like we saw in last class, if we put a resistor RE, then this variation, a part of it will be absorbed by RE, and therefore VBE, across VBE it will not appear, or a very small part will appear. That will not lead to that much change in the IC, and therefore Vout does not change. But now you can say that, okay ma'am, then what about the original input? My original input is also changing, and I want that change to appear across VBE so that my IC changes and my Vout reflect the change, because that is why I am making the amplifier for. That is true. That means in that case also a part of your actual perturbation will be taken by RE, and that would mean that RE will actually decrease the voltage gain. That is the problem of RE. That is why it is called a degenerated resistor. It degenerates the voltage gain. So reduces voltage gain, but it increases stability and linearity, which is very important. Linearity means whatever you put it input and output, you should get the same thing, similar thing. So how much of input is getting replicated back at output with the gain. Okay, so decreases voltage gain but increases stability and linearity. We will see that it increases input impedance as well, and it also increases output impedance, and we will see what is the effect, whether there is a problem or not. You understood? Any doubts? We put RE so that unwanted changes in input does not reflect the output, but input changes which we wanted changes in the input, that will also get absorbed by RE, and that is why there is a decrease in voltage gain because of the presence of RE, and that is why it is called a degenerated resistor. We will also see how to mitigate this. Okay, but this increases stability and linearity, therefore use of RE is very common. Increases input impedance, increases output impedance. So please write these points. I am giving you 1 minute, and then we will start with the small signal model. Or let me just make the model, and till then you guys can simply write it down.
10, ma'am.
Now please start solving this circuit to find Rin and your AV. So first find AV, then find Rin, and then see R out. So take R naught to be infinity. That means this resistance is not present. Okay. So now I'm not going to put KVL now. So I have already told you how to solve it. So now please try solving this. Oh, there is one mistake. This should be open. Yeah. IB, IC. This is IB plus IC, right? So just solve it. I'm not writing it down. I'm giving you 5 minutes. Try solving it. I hope you are able to solve. If you are not, then please let me know, okay? Okay, so let me start solving. Or anyone wants to tell the equations? Input KVL. So you see now in this kind of question, GM Vpi is coming right from here. GM Vpi. This is open. Okay. So and here IB is coming. So now you can put a KVL in the input loop. So V in will be equal to IB R pi or V pi. So I am writing V pi. V pi plus IB into, sorry, my internet is actually very weak. Okay. RE into IB plus GM pi. Is this clear? Now IB is what? IB is nothing but V pi by R pi. Okay. So therefore V in is equals to V pi plus RE into V pi. I am taking V pi common. 1 by R pi plus GM. Clear? Let's have a look. Therefore, V in will be equal to, which V in was actually equal to what in earlier case? It was V pi R pi. So that V in equals to, V in was equals to V pi in the earlier case, right? So now V in equals to V pi 1 plus, so let me write R pi plus RE 1 plus GM R pi upon R pi. Correct? So let me have this as first equation. The other one will be that V pi by R pi is nothing but IB, right? So therefore V in equals to IB times R pi plus 1 plus GM R pi into RE. Okay, and therefore RN is nothing but what? V in by IB, right? See the small signal. V in by IB is nothing but your RN. How is it? I had explained it before. Two-port network. V in. So the entire circuit is here. The entire small signal is here inside this. So V in by IB is your RN, which is equal to R pi plus 1 plus GM R pi into RE. You would have also seen it this as R pi plus 1 plus beta times RE. So your RE has basically increased your input resistance by a lot, right? By many folds. If RE is 1 kilo ohm, beta is 100, your input resistance increased by 100 ohms, 100 kilo ohms, which is a huge value, right? So RN is increased. Okay. So now what is V out? V out is something which is here. So V out is nothing but minus ICRC. IC is nothing but minus GMV pi RC. Just take a look. Minus GMV pi RC. Now you know what is V out by V in by V pi, you know. We had seen, right? So V out is equals to minus GM RC into V pi. Now you have seen from here equation 1, V in by V pi. Is this clear? Whatever I have written. From equation 1. I've just substituted V pi. Now please write down AV. Please find and write down AV. What is AV? V out by V in. Not minus sign will not be there since I have put a mod. So GMRC upon divided by R pi 1 plus 1 by R pi plus GM into RE. Now if GM is very greater than 1 by R pi, because R pi is normally in kilo ohms, right? So GM, if in case if GM is very greater than R pi, then we normally use this formula. We don't use the previous one. We don't use this one much. Okay, we don't use this one much. What we use more is this one, GMRC upon 1 plus, if 1 by R pi is smaller, it is neglected, GMRE. Okay, this. So this can also be written as RC upon 1 by GM plus RE. Now this is what will be mostly used to approximate the models and solve without using small signal. So please write down these steps and then I will explain you some more. Please write this down. Okay. Uh, Please let me know once you are done. Okay, now we have to finish it quickly. Okay, so now that means that in this transistor, okay, the one that I had drawn, where is it? Yeah, in this transistor, if I have this emitter resistance here, then what happens is the gain is basically now the output resistance. Okay, so let me just put it in this way because this has come in gate. So if I draw my transistor like this, okay, so earlier you had seen two things. First was AV was GM times mod AV, okay, RC, right? That was the first observation. Second was in the presence of early effect, mod AV is GM into RC parallel R naught. That is what R naught does. It comes in parallel to RC and that is what GM is. So these are also called intrinsic gain. Okay. So suppose if RC is not present, then due to early effect, AV is equals to GM times R naught. RC absent. This is called intrinsic gain. Okay. Now for ease of our solution, we neglect R naught. If R naught is present, even if RE is present, R naught will only come in parallel with RC. The presence of R naught does not change anything else. It only comes with parallel with RC. Okay. So now see, this is the second answer. Now if you follow, you will see that what is this? What is actually happening? How did we get GMRC? When we were solving, we had actually got GM R pi RC in the numerator and then we had got R pi in the denominator. This is what we had got in the first small signal. You solve it again and you check. Okay. So what you get is this. Then R pi cancels out. So what is this? This is nothing but beta into RC upon R pi. Correct? Understood? This is nothing but beta into R out by R in. Did you get it? This is nothing but R out by R in. Okay. And therefore, when even in the presence of RE, what is happening? When the presence of RE, if I now use this formula, beta into R out by Rn. So beta into Rc upon what was Rn? R pi plus 1 plus beta Re. Just the one that we just saw. I hope you are following me. So now you see, now you approximate beta Rc, and this term, this 1 plus beta Re will be much higher than R pi. Whenever beta is multiplied into something, it automatically becomes high. So then this is approximately equal to beta Re. 1 plus beta is approximately equal to beta. Beta is 100. So 1 plus 100 is 101. Approximately equal to 100. So now you see what it is. RC by RE. Is it clear? Please respond. Is it clear till here? I want a response from you guys. Clear, right? Okay, good. So now there was one question in gate in which RC was given, let's say 2 kilo ohm. I don't remember the exact value. And RE is 1 kilo ohm. And they asked AV. And nothing else was given in the question. So if this is how the question is framed, if nothing else is given and this is how the question, this is the only question, only this much, and nothing else is given, because then you will be thinking, array, how will I find it out? This is not given, that is not given. Or if some of the parameters are given and still you think that it is, you are unable to find out, then there is no other way than to simply divide. Just divide RC by RE and you get the gain. First point. You understood what I'm saying? In gate, this kind of question can come. There won't be any other data which will help you in finding out the voltage gain, but only these two values will be given. You simply divide, you know the answer. Second thing, if a lot of parameters are given and you can use those parameters to find out gain. Okay, do that. But what will happen? You just first see RC and RE. When you observe RC and RE, you know that okay, the maximum my answer can go is 10, 2. Maximum my answer can go is 2. Plus 2 is the maximum thing my answer can have. Am I correct? That is your intuition. So now even when you are solving the question, even you are step by step solving the question, and suppose you came to a value -4, you already know it's wrong. You know that you have done some silly mistakes. You understood what I'm saying? In gate it is very important. This is helpful in cross checking what you are doing. This kind of circuit. Am I making sense? Please respond. So this can be used in two ways. First, that is given, you are directly finding out the answer if something else is not given. Second, other parameters are given, you can solve them, find the gain, but with these values you already have an intuition that okay, this is what my voltage gain should maximum come. So when you will be solving, you might be ending up with -1.8, 1.7, values like that. But it won't go something above 2. It won't go. Am I making sense? Is it fine?
Yes, ma'am.
Making sense, right? Okay, so now Kothari Gopinath has asked, ma'am, what is the reason for getting 180-degree phase shifted output in CE configuration? Okay, I'll tell you. Okay, let me just finish. I will tell you. This is due to the basic nature of common emitter. Okay, so yeah, so this is the another thing. Now, one more conclusion that you can have. You see, this is basically what? RC by 1 by GM plus RE. That means when I say RC by R in, what I mean is the resistance looking from here. I should not write R in actually. So let me just say the resistance looking from here. And the resistance looking from here. So if I divide both the resistances, I should get. So what is the total resistance? The inherent resistance of BJT will also come. So the inherent resistance of BJT is 1 by Gm. Okay. So 1 by Gm plus Re is in the denominator, and in up numerator RC is there. Is this fine? The inherent, because there is a current source that will provide a impedance of 1 by Gm. So that 1 by Gm added to Re, because both are in series. There is no concept of parallel. Both are in series. So 1 by Gm plus Re is what is showing coming in the denominator. With this concept, we will quickly solve one question. Till here, I think it is fine, right? Now, suppose I have this figure. So in this figure, what will happen? If the value of C1 is very large, that means around infinity. Value of C1 is very large. In DC, what will happen? In DC, this is open. So the constant current source will bias it. Okay, in DC the C1 will be open, so the constant current source is present. It provides a hardwired, i.e. the BJT is biased. This is another way of biasing BJT. Okay. Now if the capacitance is present in other frequencies and if the value is high, then it will work as a short circuit. Okay, and now the entire circuit is similar to what you have done earlier. So don't get confused. Okay, so voltage gain, input output impedances are same as what we have just calculated. Okay, another concept. I have just written that AV will be equal to GMRC upon 1 plus GMRE. This is what we had seen, right? Approximately equal to. Huh? And I also told you that AV is equals to capital GM into R out. Now I know that R out is nothing but RC, and if R naught is present, it will come in parallel. So RC, so that means what is GM? This is called degenerated GM. So because of the degenerated resistor in the transistor, because of emitter, the transconductance is what is actually decreasing, and therefore the overall voltage gain also decreases by the same factor. Okay, it is because of the transconductance. Clear? These results are very important. Please take a note of all these results that I have written. This one especially, you just write it down. After that, we will quickly do two questions related to this. Done, right? Should I move forward?
Yes, ma'am.
Okay. So now, where did I write those two questions? Okay, let me just first do this one. Okay, quickly write down this circuit. Draw the circuit and then I'll just tell you what is happening. So in this circuit, if you see, again C1 that will be shorted. Once C1 is shorted, what will happen? Okay, okay, and what will happen since I'm talking about AC signals? So then VCC is shorted and the I1 is open. Okay, so now this is the same circuit as we had seen, right? So R2 is now in place of RE, and what will be your output resistance? It will be RC parallel with R1. Just check whether I am making sense or not. So I wanted to introduce the concept of capital RB, but we don't have time. We'll quickly do two more questions. So just check this one and let me know if we have to move forward. Then I will quickly finish off the other one. Should I move to another question?
Yes, ma'am. Continue.
Okay. So, okay. So another question we have. Now in this question, if you keep on drawing the small signal model, it will be very tedious. Okay. So just see if you guys are able to understand how to solve it without drawing the small signal model. And tell me if if any one of you get an idea, just tell me what you are thinking. Then we will see if it is correct or not. Okay. So again, the voltage gain. You have to find the voltage gain. Any one of you? Any idea? So you need not make the small signal model. You can just solve this. 2 minutes more, just think about it. You will have to use the internal resistance of the, you will have to use the input impedance of the second transistor. So now if any ideas are there, this is the hint. So you have to use the input impedance of the second transistor. Any ideas, anyone? No? Okay. So whenever this kind of question is there, see what is this emitter resistance will actually see. What will this terminal see? This terminal is seeing one RE and another input of another BJT. So input of another BJT, what will be it? If it is a two-port network, suppose I don't have this BJT here. I don't have this BJT. Okay. I don't have this BJT. So now what I have is a black box. So what will actually matter? What will actually matter is what is the resistance impedance here with respect to ground, right? So now I'm replacing the black box with what is actually there. What is actually there is a BJT. So what is the input impedance of the BJT? There is nothing else. There is no other connection. So Zin is R pi 2. If this is Q2, this is R pi 2. And therefore V out is, the way we had seen it, it was RC by 1 by GM plus RE, right? So now what it will be? The emitter resistance is now having R pi 2 in parallel to it. Clear? So V out is this clear? Anyone who had thought of in this line? If you are thinking in this way, then your thinking was correct. Okay? Okay.
Ma'am, how to find R pi? Is
How
it
to?
given?
Oh, it will be given in the question. Something will be given in the question to find that out. Okay? So what right now matters is how to solve this, like basically kind of the derivation thing. So these kind of questions can be asked. Okay. Another way to solve it is, so another type of question that can be there is, suppose if I don't connect it here and I make the connection here, then how it will be? Then what is the change? What should I write? Anyone? Yes, RC parallel with R pi. Good. So RC parallel with R pi 2 and below it is 1 by GM plus RE. That's it. Okay. So let me see one more question. So Razavi's back exercise is full of these kind of problems. Okay, this is a good thing. So I'm giving you one question. You guys solve it. Okay, and let's discuss it in next class maybe, or you just try to solve it. Uh, I'm giving you the question. Please write it down. A C stage is biased at a collector current of if the circuit provides a voltage gain of 20 with no emitter degeneration and 10 with emitter degeneration, determine RC, RE and input output impedances for beta 100. Okay, so solve this question, and let me see if there are some other question as well. Okay, I wanted to introduce the concept of RB, base resistance, but I don't think I'll be able to do it in this class, so we will continue with that in next class, and then we will finish CBCEC as well. Uh, okay, yeah, one more effect that I was talking about, that the emitter resistance is 1 second. Okay, so if you consider the effect, we will see this also in next class. So if we consider R naught in the circuit, we will see that the output resistance also gets amplified with the factor of RE. We'll see that in next class. And but the high output impedance actually is used in circuits like current mirror or to design current source. So if I just now keep on talking about it, you will not understand. So we will do that in next class. Okay. So next class we will see the effect of base resistance, we will see the effect of transistor output resistance, and then we will quickly finish off CBCC. Okay, and meanwhile please solve this problem. Okay, try to solve this problem and see what answers you are getting. So you know how to solve this question, right? So there is two condition given. One is that without emitter degeneration you have a gain of 20. With emitter degeneration, you have a gain of 10. That is, the degeneration factor is reduced by a 2. So, with degeneration, the gain is GMRC. With and without without degeneration, it is GMRC. With degeneration, it is GM by 1 plus GMRE into RC. Okay. Now this is given as 10. This is given as 20. This is given as 10. Right, that means 1 plus GMRE is 2. So this is how you should start. Okay, so with this please start, find the value of REs. Okay, the current, collector current IC is given, therefore you can find GM. Once GM is there, from this derivation you will find capital RE. Once capital RE is there, GM is there, you already have gain, so you will find RC. Once that is there, beta is given, GM is there, beta is given, you can find R pi. Once that is there, R out is nothing but capital RC. Clear? Early effect is not there, so R naught is infinite. Is it clear? Now coming to the question that was asked, that why in common emitter the phase is 180 degree shifted. So what happens is, if you write down the equations, what is V out? What is V out? It is VCC minus ICRC. And what is IC related to? correct? That means a small change in your input which brings out the change in VB, that leads to, that is amplified by a factor of GM, which is the transconductance gain, and is reflected to IC. Huh? So IC also changes by the same amount. So if your delta VB increases by a small amount, IC will also increase. Now if IC goes up, what will happen to V out? It will go down. Understood? So the effect, so VCC is just a constant, right? So therefore, if I consider VCC to be just a constant, you see what is delta V out? Delta V out is nothing but minus delta IC RC, right? So if IC increases, the V out increases, but with a negative, different phase, with a 180-degree phase shift in the opposite direction. So that is the reason why the negative sign occurs. Okay, that is the logical reason. Mathematically, obviously, when you solve, you will get the negative sign. But this is the logical reason. Am I correct? Making sense? Okay, great. Okay, so then with this I will end up. Next class I won't be able to join. Next Saturday I cannot take class. That's why today I took a 2-hour session. So 28th I am not taking a class, but I will finish it off on 4th. Okay, so 4th we can again have a 2-hour session and finish it, because I think 4th will anyways be the last session of this series. So 4th I will take 2 sessions together and finish it off. Okay. Okay, so if there are no further questions, I will wrap it up. So please let me know. Okay then. Okay, then we'll wrap the class. Thank you. Let's meet on 4th.